In this section, we're going to talk about what actually happens in the nucleus when it goes through any type of radiation. Okay. So anytime an unstable nucleus emits an alpha or beta particle, it's actually going to change the number of protons and or the number of neutrons in that nucleus. Okay, so this is where it gets a little bit weird trying to think about it. So an example, you have radium-226 is going to change into radon-222 by emitting an alpha particle. So remember, an alpha particle is 4 total mass numbers, okay? So it's 2 neutrons, 2 protons. And the 226 and 222 are mass numbers for their respective atoms, okay? And so you'll notice radium emits the alpha particle, so it's losing 4 mass, okay, to become 222 mass total, right? So that's where you get the 226 to the 222. But then at the same time, it's also losing 2 protons. So you have to decrease the atomic number by 2. Okay, so that's where you get it changing from radium into radon. Gamma decay, on the other hand, only changes the energy of the nucleus. So you're not going to have any change in the atomic number, the number of protons, or any change in the atomic mass of the element. So you're not changing the number of neutrons, not changing the number of protons, not changing the number of electrons. It's just the energy. So it's really simple, okay? Everything basically stays the same. With nuclear decay of beta decay, this is where things are a little bit funky, okay? So the atomic number is actually going to change during beta decay. It's going to actually go up by 1, okay? So this is where, again, things are a little bit strange. So a beta particle is actually released when a neutron decays to form both an electron and a proton. Okay, so neutron has a neutral charge, and it's breaking apart to form an electron, which has a -1 charge, and a proton with a +1. So it's still a net neutral charge here. Okay, but now you've lost 1 neutron and formed an electron and a proton. So you're still going to have the same mass, because remember, a proton and a neutron have the same mass, and an electron doesn't have mass. Okay, you still have the same mass, still have the same overall charge. But at this point, the proton is going to stay in the nucleus. So that's going to increase the atomic number, the number of protons, by 1. On the other hand, the electron gets released. That's the beta decay part of it, okay? So the atomic number, the number of protons, will increase by 1. All right? So for an example here, carbon-14 undergoes beta decay. So it's going to actually release an electron by breaking down one of its neutrons into a proton and an electron. So it releases the releases the electron and keeps the proton. So your atomic number is going to increase. So you go from carbon, which has 6 protons, to nitrogen, which has 7. Okay, so this is kind of how you see that. Beta decay is you're going to have the electron leaving the nucleus. So it's going to be one of the products. Okay, so you start off with carbon-14, has 14 mass number, okay, 6 protons, and then you lose your beta decay, which is right here, the 0 over -1e, and then basically you just figure out what's left. So you want to go across the top, okay, with the equal sign where the arrow is. So you've got 14 equals 14 plus 0 on this side, okay? And then if there's any x there, like basically say this was 14 over 6c, yields 0 over -1e plus x. Okay, and x is some atom. You have to figure out the number of protons, the element of that atom, and the mass number. Okay, so it's 14 equals 0 plus x, just looking at the top line here. Okay, so x is obviously 14. But then you have 6 equals -1 plus x. Okay, which the x would be right here where that 7 is. Okay, so in order to get rid of the -1, you have to add 1 to both sides, which means that that is how that 7 is a 7. Okay, so let me try to write that out, make it a little bit easier to understand. So you have 14 over 6c is going to yield x, we'll just say x over y z, z is your element, plus 0 over -1e. Okay, so you go across the top, you take your top numbers, so 14 equals x plus 0. So x is obviously 14. Okay, and then you do the same with the bottom. So you have 6 equals y minus 1. So you add 1 to both sides, and you get that y equals 7. Okay, so now you have 14 over 7. You look at your periodic table and find element 7, and that is a nitrogen. So that is what goes right here. 14 over 7N. So, with alpha decay, you're actually going to have both your mass number and your atomic number changing. Okay? So, for an example here, I'm going to do the same thing that we just did. Okay, so I'm going to leave this number right here as x over y and a capital Z. Okay, so we have, going to add up our top numbers, 226. We've got the arrow here, so that's where the equal sign goes. And it's going to be x plus 4. Okay, subtract 4 from both sides, you get x is 222. Okay, and then you do the same thing with y. So you have 88, got your arrow, so that's where your equal sign goes. And then you have y plus 2. Subtract 2 from both sides and you get 86 equals y. Okay, so then you put 222, don't know why my computer keeps screwing up here, over 86, you look up what your 86 element is, and you get Rn. So that goes right here. Okay, so this is just showing you how you get that again right there. All right, so radioactivity was really discovered, or the research was really done by a married couple, Marie and Pierre Curie. Marie was Polish and Pierre was French. They met at school and got married. Pierre was also a scientist, so they actually worked together for quite a long time until Pierre was killed in an accident. But they really made a lot of discoveries with radiation that really nobody else was doing that kind of work at the time, especially not women. Okay, Marie Curie remains to this day the only woman to have 2 Nobel Prizes in 2 different sciences. Of course, Marie Curie is, well, she's not just the only woman to have won 2 Nobel Prizes in 2 different sciences. She's the only person to have done that as well. Sorry, there goes Potter. Of course, her work in radiation is most likely what killed her, especially because at that time they didn't realize how dangerous it could be. It was just kind of a new scientific phenomenon, and so, you know, they didn't really take a lot of precautions that we would nowadays. So, for an example, she often walked around with uranium in her pockets, something that if you did today, you would be called a terrorist. So I don't suggest it, especially because it actually gave her a bone disease that she did die from. So, yeah. All right. So, while it's impossible to predict the moment when any particular nucleus will decay, they can actually predict the time required for half of the nuclei in a given radioactive sample to decay. So these are called half-lives, okay? So a half-life is a measure of how quickly a substance decays. So in that substance's half-life, okay, if like, say the half-life is 10 years, every 10 years, half of that substance will have decayed, okay? So it doesn't happen all at once. It's not an immediate kind of thing. Oftentimes the half-life will be, you know, a significant amount of time, so you get like low-level radiation released over time. Okay, there are some nuclei that have a very, very short half-life. Okay, so they will decay at a much quicker rate, but different radioactive isotopes have different half-lives. Okay, now this depends on the isotope itself. So any atom of carbon-14, for example, will have the same half-life. Okay. So doctors and scientists can use isotopes with short half-lives. One example would be iodine-131 to diagnose medical problems or tag proteins for study. These are isotopes that will decay relatively quickly, so all they have to do is look for that specific type of radioactive decay, and that will tell them where the disease is or where the protein that they're studying is. Half-lives can also be used to estimate how old an object is. So this is where you get into the carbon-14. So in this case, you need isotopes with long half-lives, okay, especially if you're dealing with more than just a couple thousand years. Okay, so potassium-40 or carbon-14 are most commonly used for this. Potassium-40 actually decays to argon-40. So rocks with a higher argon content are older than those with potassium content, okay? Because these are rocks that don't actually contain argon to begin with, okay? So any argon that's present in the rock came from potassium, okay? From potassium-40 decaying. So radioactive decay rates, okay? So this is looking on the right here. It's looking at the different types of nuclear radiation that are emitted. And then also on the left, you can see the isotope and its half-life. So you have, that's supposed to be thorium. Thorium-219 has a half-life of 1.05 times 10 to the negative 6 seconds. That's a really quick half-life. Okay, so it goes like that. And then if you look all the way up to uranium, it actually has a natural half-life of 4.47 times 10 to the 9th years. So, you know, 9 zeros after the 4, that's, you know, quite a lot, okay? You also have carbon-14 there in the middle, that is 5,715 years, okay? And then various other ones here. So radon, 3.82 days, so almost 4 days. Iodine-131 with 8 days. Okay. Now remember, when we talk about the half-lives, the isotopes, the atoms, are still decaying during that half-life. It's just saying that by this time, so for the iodine-131, by the time you get to 8.1 days, half of your iodine is gone. Half of it has decayed. Okay. So you only have half of it left. And then in another 8.1 days, you have half of that amount left. And so on and so forth until it's pretty much all gone. Okay? So we're going to pause here and pick up in the next video.